Hello again, my dear students, and welcome to this second part with our first lecture dealing with power amplifier and our output stage power amplifiers. If you remember, my dear students, we have started together in the first part our models related to what we can call a class A power amplifiers. Today, we are going to start with class B power amplifiers. So please permit me to share my presentation slides and go directly to the start of a class A power amplifiers. Before proceeding, let's remember together what was the main concern towards the class A power amplifier. Class A power amplifier was very efficient in terms of the operation period, as it's operate across the 360 degree of the input, as you can see. However, the problem related to the power consumption was detected as the major problem related to class A power amplifier. In a class A power amplifier, the maximum recorded efficiency was 25%. Herein, efficiency is defined as the percentage of the power reaching load to the overall power supplied by the two suppliers. Now, what we are going to do is we are going to demonstrate another approach of implementing output stage power amplifier. And this approach is related to the class B power amplifiers. This is the basic schematic for a class B power amplifier. And before going into details, let's very quickly scan together the difference between this architecture and this architecture, or what's called an NPN architecture and PNP architecture in terms of the operation. So I will now turn to my whiteboard in order to start demonstrating this together. Okay, so if you remember, my dear students, we have started together the concepts of bipolar junction transistor with this architecture. So this is called the collector, and this is the emitter, and this is the base. Basically, for NPN configuration, electrons are going through the emitter to the collector. So the motion of the electrons is from the emitter to the collector, of course, if the bias voltage is sufficient enough. And in this case, the current is flowing from the collector to the emitter, because current is defined as the anti-direction of electrons. So that's why the current is flowing in this direction. And that's why we have this arrow in this direction indicating that the current is going to the emitter, as you can see. This is what's called the NPN configuration. Alternatively, for the PNP configuration, we have something like that. So this is P, this is N, and this is P. In this case, current is flowing, or Hz is flowing from the emitter to the collector, and the direction of the current is similar to the direction of Hz. That's why your arrow is outgoing from the emitter, as you can see. So for NBN, the condition of operation is related to the PE, or the base emitter junction. You have to put a base emitter VPE voltage, which is equals to or sufficient to the building voltage of this node, which is roughly 0.7. So this VPE should be 0.7 in order to operate. In other words, the voltage of the base should be higher than the voltage of the emitter by 0.7 in order to operate. And this here includes two regions of operation, either in the active region or in the saturation region. I think we already consume sometimes to understand this in class A power amplifiers. Now, for a PNP, it's vice versa. So the voltage of the emitter here should be greater than the voltage of the base by 0.7. So either to say VEP equal 0.7 or to say VPE equals to negative 0.7. In all cases, what we are searching is that the voltage of the emitter should be greater than the voltage of the base by this 0.7 or the building potential VBE node. Okay, so why we mentioned this? Let's turn back to our schematic. Okay, here, and let's turn again our laser pointer. So, as you can see here, my dear students, this structure depends on two types of bipolar junction transistors. The one in the top of the schematic, this one, which we call it QN, is equals to, or it's an NBN transistor. That's why we, in order to make this transistor operates, the voltage here in the base should be greater than the voltage here in the emitter by 0.7. Alternatively, this QP, which represents the PNP transistor, because why it's a PNP? Because simply the arrow here represents a current outgoing from the emitter, as you can see. So in order to make this transistor operate, you have to have a voltage on the emitter greater than the voltage on the base by 0.7. So that's why we have this combination. Okay, so let's start the theory together. Basically, if this input is equal to 0, then basically this current will be equal to 0. There is no output, and this point will be grounded. No current flowing in this branch. This point will be 0, and this point is 0. In this case, both transistors are turned off because simply this is 0, this is 0, and this is 0. So here VPE is equals to 0, and here VEP is equals to 0. Now, what will happen if? What will happen if this V input starts to increase gradually in a positive direction? So let's say that this is 0.2. So let's start using them. So let's say that this is 0.2. I'm sorry. This is 0.2 voltage. Let me try to write it in a better. This is 0.2. So this is 0.2 voltage in positive, I mean, positive 0.2. So simply, this is similar 0.2. And this is still 0. And of course, this is also 0.2 because this is the same node, as you can see. Now, this VPE, or the voltage between the base and the emitter for the N transistor, is positive, yes. But it is still below the built-in. Let's assume for this example that the built-in is 0.5. So it's positive 0.5. So it's positive 0.2. So it's positive. The voltage in the base is greater than the voltage in the emitter for this QN transistor. However, it's not still sufficient to make this PN junction forward. So still QN is off. On the other hand, this voltage, again, this voltage equals to 0, so it's still ground. And this is still 0.2. Here, the voltage of the base is greater than the voltage of the emitter, which is against the operation of this transistor. Because in order to make QP work active or turn it on, you have to have the emitter voltage greater than the base voltage. However, in this case, the emitter voltage is 0 and the base voltage is 0.2. So it's totally off. So that's the first case. Now, let's assume that this voltage starts to increase a little bit. So this voltage, which is the input voltage, turns to be plus or positive 0.5 voltage. Now, when this voltage is 0.5, positive 0.5, so typically this is the same voltage. And again, please remember, this is still 0. Okay, now your QN transistor will turn on because simply you give a base voltage greater than the emitter voltage with the value needed to make this QN turn it on. However, QP will be totally off because this is 0 on the emitter, and on the base we have the same voltage of 0.5. And as I mentioned, this is against the operation of the QP because QP is seeking for a voltage on the emitter higher than a voltage on the base, which is not the case now. So this QP is turned off. So what will happen simply, my dear students, is as far as this input voltage is 0.5 or higher, your circuit will be turned to be something like that. So this is the VCC, and this is QN, and this is the input, and this is the output, which is typically this part of the circuit, as you can see here. And if you remember, my dear students, QN, or if you remember class A power amplifier, this is typically what we called an emitter follower, because simply in this case, our emitter will follow our base. So V output equals V input minus VPEN, and we call it VPEN simply because this is related to the N transistor or the QN transistor. So whenever the input increases, the output increase with a linear slope and with a shift equals to VPEN, or that is this 0.5. This happened when the voltage is 0.5 or greater. What about the negative half cycle? What about if this voltage here is, for example, negative 0.5? So if this voltage is negative 0.5, now, again, remember, this is a grounded point. So now this transistor can be turned on because the voltage of the emitter is greater than the voltage of the base by an 0.5. This is a 0 on the emitter and a negative 0.5 on the base. Alternatively, for this QN, you can find that this is still negative 0.5, this point, and this is 0. And of course, this is again is the operation of a transistor, because in an NPN transistor, your base should be greater than the emitter by 0.5. So this transistor will be turned off as far as this input voltage is negative 0.5 or lower. And what will happen here is we keep with still an emitter follower, but in a different way. Now, the voltage of the output, V output, equals to V input minus this VPEN, but it's basically minus positive, so V output equal V input plus VBN. That's results with, results with, let me open the pointer again, okay, with this. So if the this is what we call a characteristic curve. A characteristic curve is a curve relating the input to the output. So if the input is 0.5 or greater, this QN will turn on and you will have a positive slope, as you can see. If this voltage is still below 0.5, so basically QN turned it off, QP already turned it off. QP will turn on when this voltage will be smaller than or equal negative 0.5, as you can see here. So this what we call that band in between your operation. So this is a basic difference, my dear students, between class A and class B. In class A, we didn't observe such a dead band. However, in class B, as you can see, there is a dead band between VPEN and VPEB, where both transistors are turned off. But let's think about another issue, which we already considered, my dear students, in our previous sections related to class A, which is what are the boundary limits for this output. If you remember, my dear students, these boundary limits related to the saturation. So, for example, QN can operate in the active mode as far as its VCE is greater than or equal VCE SAT. This is VCE. So as far as VCE is greater than or equal VCE SAT, it will turn on, or it's still in the active mode. So, which is the targeted mode, of course, for in our case. So in this case, VC represents the VCC and VE, or the emitter voltage, represents the output. So simply VCC minus V output equal VCE SAT. Or in other words, V output equals to VCC minus VCE SAT for the N transistor, as you can see. Typically, the same happen when you consider the VEC for the NBN transistor. So here, VE represents the output and VC represents the negative VCC, and your minimum value should be VCE SAT. So you can have a similar boundary here, as you can see, for your voltage. So your transistors will have a boundary limits related to the saturation mode, which is typically the same as in class A. But actually, what is maybe new here is the observation of this dead band where both QN and QB are turned off. The first question may come to your mind now is how this dead band defect our operation. You can see the answer here. When you have an input, smooth input signal inputted to your power stage power amplifier, your signal will be first clipped with the boundaries of VCC minus VCE SAT up and down, which is normal as a class A. But what's new also is this distortion, as you can see here. This distortion appears simply because you have a dead region at which there is no gain. Input is multiplied by 0, so the output typically is 0. That's why this transfer function is very important to illustrate the operation of our power stage amplifiers. Maybe in the next stages during this lecture, we are going to discuss how to minimize this dead band, or some sort of operations or ideas or tricks, let me say, in order to minimize this dead band. But before going into that, one may ask a question: why we use a class B? In class A, we don't have such a dead band. So where is the advantage of the class B? Simply, advantage in class B is a disadvantage in class A. If you remember what we consider as the efficiency of the stage, which is defined as the power reaching to the load with respect to the power supplied by the suppliers. So let's now start to calculate the power efficiency of these class B power amplifiers. So again, the efficiency is defined typically the same as in class A power amplifiers, where we have the efficiency of our stage equals to the power supplied to the load over the overall power supplying by the two suppliers. In order to make this mathematical calculation easy, let's ignore this distortion effect and assume that the output is a typical sinusoidal wave. So simply, the power can be determined typically the same as in class A. knowing that the maximum is V output, so it's a V output over root 2 to determine the R root mean square value, square V square over RL, or simply half V output square over RL. Now, what about the suppliers? Simply, we have two suppliers. The first supply, which is positive VCC, and the second supply is a negative VCC. However, these two supplies are not working during the whole operation. And during the operation or during the working operation of each supply, its current is variable. Simply, if we are in the positive half cycle and this Qn is turned on, simply this QP is turned off and this is not working. In this case, the current flow in your circuit will be something like that. The whole current flowing in Qn will automatically go to the load because simply this is turned off. So you can say that the current flowing here is simply this node, which is V output over RL. But take care, this happens only in the positive half cycle. So if you would like to make a chart for this current flowing, it will look like that. And so on. So in the positive half cycle, in this cycle, your supply is turned on and it's applying a current equals to V output over RL. In the negative half cycle, this Qn will stop working and it will turn off. Alternatively, the lower supply here or negative VCC will have an anti-operation. So in the positive half cycle, it will be turned off, and in the negative half cycle, it will work or it will drive a current. That's mean that each of these two supplies is working half of the operation, only half of the operation. Again, we are assuming that the effect of the dead band is neglected to make mathematics easy. So each transistor is working the first or is working only 50% of the operation with a current equals to V output over RL. If you remember, my dear students, this is what we call a half-wave rectified signal. So back to mathematics, in order to determine the root mean square of this half-wave rectified signal, just turn over, yeah. So if you remember, this was 1 over pi V output over RL times VCC. So VCC is the voltage. V output over RL is the maximum value for the current. And this 1 over pi is the normalization or the transformation factor from maximum to root mean square, same like when we divide here by root 2. So simply speaking, this is the power driven from each supply. As we have two supplies, so the total power driven is 2 over pi V output over L times VCC. Now you have the total power supplied. You have the total power reaching the load, so you can calculate the efficiency. Herein, you will end up with a maximum efficiency of 78.5%. And I think now we answer the question, why we agree to have this dead band. This is simply that trade-off appear in our design. In a class A power amplifier, we have 100% operation. The operation is working across the 360 degree. However, the overall conversion efficiency or the power or the efficiency of the stage was very low. Its maximum was 25%. Alternatively, in a class B power amplifier, we have a problem related to the dead band appear in the middle of the operation, which makes the boost transistor off for a certain band of voltage. However, we push up the efficiency maybe more than 3 times to reach 78.5%. This is simply the variation between or the trade-off between class A and class B. So we can estimate now or calculate the power dissipated in the transistor, which is simply the power not reaching the load. So it's a subtraction between the supplied power and the load power. We already determined both the supplied power and the load power. So this is the maximum value, or here we can make some sort of differentiation for this PD and equalize to 0 to search for the value for the output for maximum dissipation. So this is 2 over pi VCC. So if your V output reaches the value 2 pi over VCC, in this case, you will dissipate the maximum dissipated power in transistor, which is equals to 2 VCC square over bar square RL square. Of course, this dissipated power is among both transistors, Qn and Qp. So the dissipation for each of them is typically half this value, which is VCC square pi square over RL. This is the maximum power dissipated by a transistor. That's why we don't have this 100% efficiency, which is, of course, something hypothetical. And we have a limited efficiency of 78.5, which is still very large with respect to class A. So this is the main concept of operation of class A, of a class B, sorry. So you lose some sort of operation by this deadband, but you boost the overall efficiency of your transistor or of your amplifier. Okay, so we have now demonstrated the pros and cons of class B, and it's easily observed that the main con here is related to that band. And obviously, our next move will be how to minimize the effect of this dead band. Actually, this will be detailed answered in class AB operational amplifiers. That's why we call it class AB, because it's some sort of a hybridization between class A and class B. But before moving to class AB, which will be most likely in the next part of this lecture, but there is some tricks implemented in literature toward still using class B, but with minimized band or dead band. One of these tricks is this schematic. Herein you are using this differential amplifier. I think you already have studied differential amplifiers deeply in electronics 1 and electronics 2. And you can return back to my lectures for electronics 1, I think, concerning the differential amplifier operation. And I think already in electronics 2, you have studied more detailed manner on that. So this differential amplifier will act to somehow minimize the impact of this dead band. How will this happen? This is simply assuming that we are in the dead band, so this point is equal to 0, the output is grounded, so this output will be equal to 0. The input will, for example, be, let's say, 0.1, for example. If we are considering some sort of a gaining factor over 5, so simply by differentiating this input, it's 5, 0.1 minus 0, which is 0.1, times 5, this will be 0.5, and this 0.5 will turn your Qn on, and still Qp equals off, is off. Similar will happen when this input is negative 0.1, it will be multiplied by 5, then it will be negative 0.5, and then this will turn on and this off. What will happen here is, assuming that we have a 5 gain unit here, that you minimize your dead band from being from negative 0.5 to 0.5 to be from 0.1 to 0.1. So you still have a dead band, but this dead band has been limited or reduced somehow. However, we have to be honest that it's not simple like that, because this is still a very complicated schematic of transistor. This differential amplifier, this simple triangle is not a simple triangle. In reality, it's a schematic of transistors. So you increase the complexity of the circuit from one hand. And another important point that you also lose some sort of efficiency, because simply this will work with VCC and negative VCC, and there is some sort of power dissipation here. So you cannot say that you still have this 78.5% as an efficiency. Your efficiency will be automatically reduced by using this device. So you add complexity to the system, and also you lose some efficiency, but you reduce somehow the dead band of your amplifier. So this one of the schematics for that. Another schematic is not actually toward minimizing the dead band, but it's called a single supply operation. This is also very famous. Here, this is typically the same like the first or the principal class B amplifier. However, in this schematic, you replace your two supplies by one supply. In the previous schematic, we have VCC and negative VCC. Here we have two VCC and 0. This is actually related to some advanced topic in analog electronics related to the mismatching of power supplies. Maybe it's somehow a bit advanced for this course to discuss. You can go to some of my lectures in the postgraduate lectures related to band gap voltage. I think you can find some information about that. But here you can simply make an analysis, or what I invite you to do now here is to make a comparison in terms of operation. Principally, we are doing the same process. We have an input, so whenever the input is greater than the 0.5, this QN will turn it on and this QP will turn it off, and you will have a emitter follower here. Similarly, when this input is negative 0.5 or lower, so this will turn it off, and this so this will turn it on and this will turn it off, and you will have another form of an emitter follower again. So in terms of operation, you will have typically the same operation, but maybe in terms of biasing, the conditions will differ somehow, because now this VCE, or the boundary for the VCE, will be 2 VCC minus V output equal VCE sat. So this is the boundary for or the boundary limit here for the output. So it's 2 VCC here minus V output here equals 2 VCE equal VCE sat. So the maximum limit will be 2 VCC minus VCE sat, and alternatively in the lower case you will have V output minus 0 equals VCE sat. So your lower limit will be VCE sat. That means that you DC shift your signal from being from negative VCC plus VCE sat, which is the lower limit here in the previous case, and the upper limit, if you remember, was the VCC minus VCE sat. So this was the previous limits. Now these limits will be DC shifted to be from VCE sat to VCC minus VCE sat. So you DC shift. However, this DC shift will be automatically neglected or removed by using this capacitor. That's why we use this bypassing capacitor. If you already know that capacitors are not moving DC values, that's why this DC shift will be removed later on. But as I mentioned, the main concept here is related to avoiding the mismatching in the power supplies, because in the previous model, or in the standard model, we have yeah, we can see it here even we have positive VCC and negative VCC, and the symmetry of the operation is dependent on that these two voltage sources are typically identical. So whenever this is plus 14.8, then the other one will be negative 14.8 and so on, and this is somehow not fully granted. So to avoid this mismatching, we can use this single supply operation for our class B power amplifier. So this is another version of a class B with still doing the same operation. So now we can conclude that output stage power amplifier class B. In the next chapter, or actually in the next part of this chapter, we are going to start with class AB power amplifier. And as I mentioned, our main focus in class AB will be to hybridize or combine class A and class B. So we can use the benefit of high conversion efficiency of class B and the full operation of class A. Thank you very much for your concentration, and see you later on.